Welcome to the Temporal Graph reading group today, everyone. We are very glad to host Fang Wu and Vijay from Stanford University, who will be presenting their recent work in ACL called Large Language Models Are Good Relational Learners, which gives a definitive answer, I guess. Um, and on the speaker bio side, Fang Wu is a CS PhD student at Stanford University, um, supervised by Yejing Choi and Yuri Leskovec. His research interests lie in LLMs, GNNs, and some AI for science applications. And uh, Vijay Prakash uh, Dwivedi is a postdoc at Stanford, supervised by Yuri as well. His research focuses on improving deep learning methods for graphs and relational structured data. Um, and I'm not sure who will start the presentation, but I will hand the mic to you.
Yeah, I think Vijay will do the introduction and the background. Uh, yeah.
Yeah.
Okay.
Yeah. Okay. Thanks, Andy. Yeah. So I'll be going through the introduction on, for example, the relation to deep learning and what the problem we're trying to solve for the first half. For the first few part, and Fang will take on in the details, and then he will tell more about the real LLM method that tries to answer the question on how good are LLMs as relational learners and what are some of the successful designs and experiments that we achieved, as well as what are some of the things that we tried, which we don't succeed, but then it gives very interesting limitations and maybe some further directions about how LLM should be adapted for relational deep learning. So I'll just use the slides from Fang, and then maybe Fang can do next whenever I'll just say for next. Just as a background, what we want to solve here in this work is how are large language models for relational deep learning, and with relational deep learning, we mean end-to-end deep learning on relational databases. Uh, in relational databases, relational databases as introduction is a very important area of data source because it spans many data sources in commerce, in finance, in clinical trial settings, and many scientific domains. At the very core, what's present in relational databases, like we have tables. Tables can have a certain schema, which is used to define the rows or different records in table. For example, in the e-commerce, we may have cases where I have like orders tables, order items, customers, and certain items that can be present in orders. These different items or different records in different tables can be connected through primary and foreign keys. As you can see, uh, there are some of the examples such as order ID can in orders can represent certain order items as well as customer ID in customers, which can also represent certain customers that present in orders. So this is one of the example of the connectivity structure that's given by the primary foreign key. We have in finance, we have in clinical trial similar examples. If we move to the next slide. So there are many such examples of relational data that occurs in a multi-table data setting. Multi-tabular setting. So different examples can be considered, but like why this is important is there can be a lot of prediction tasks that is of interest because this data is very huge in terms of like the number of records that's usually present in such a data source. So certain tasks of interest can be which products will a user purchase in the next 7 days, whether a user will churn from a platform in the next certain timeline, for example, the next 90 days, what will the total sales for each product in the next in within the next period of times, for example, the next 30 days again. If we move to the next slide. What will be the loan outcome? So this can be some how to say, binary prediction class that we may be interested, what will the number of total failed loans in the years, etc. So what it tells is that there are many prediction tasks of interest that is usually present in relation database, and it is not new. It has been I mean, it's a field that has been explored for maybe a decade or more, even uh, since relational databases came and since data started to be stored in this fashion. And there has been many tabular models, for example, where multiple tables can be flattened into a single joint table. Then feature engineering can be applied to create some predictive signals that can be used for some downstream machine learning models. So many of these prediction tasks are of huge commercial interest. They serve many how to say, many platforms. For example, the user churn is one of the tasks that predicts whether certain users are going away from my platform, and if yes, what should be my personalized recommendations or personalized customized products that I want to use to cater to such users. So this is just to motivate the field of relation deep learning and what it is. If you move ahead to the next slide, I'll show like how it looks like a graph. So traditionally, machine learning on relational databases, like I was mentioning, has been one of the ways to do this was to convert the multi-table data into maybe possibly a single table by flattening using the primary foreign key relationships and some of the insights that we may know about a particular domain. After that's done, usually the data is converted to some feature embedding, and then machine learning models are used. But if we look at this from the graph perspective, and why graph perspective? Because in the last 5 to 10 years, there has been much progress on end-to-end learning on graphs. We have seen the since the development of graph neural networks and and possibly the graph convolution networks in 2016, 2017 in time, there has been very much progress in end-to-end learning on graph structure data. So when we see the relational database, it is naturally a graph. So when we look at this particular schema of users, sales, and products, we can see that any record in the user table is connected to the sales, and sales entities can also be connected to products. So it looks like a graph naturally. uh, this graph is a heterogeneous graph, meaning uh, there are there can be different node uh, types. For example, there can be hundreds of millions or even more users nodes. There can be many sales node types, nodes with the sales node type, and similarly products with products node type. So we can have many rows. Each row in any table in this database can correspond to a node. And yeah, this is a heterogeneous graph by design. Generally, the these databases also have timestamps. For simplicity, it's not clear in the schema here, but generally, for example, if a sale is done, the sale is often recorded with the timestamp, and it shows patterns of how a user is interacting with different sales on a platform according to a time. So it's temporal by design, and generally it's large scale. So a relation database is by design a heterogeneous large scale graph, heterogeneous and temporal large scale graph. And if that's the case, then let's just do machine learning on a graph. So this is, this is something that has been proposed as a new framework that unifies different modeling types in different modeling aspects in graph neural network or graph learning literature, and which can be used to do end-to-end machine learning on graph structure data that's relational, that's coming from relational databases. And if we look at the task that I was mentioning earlier, they can be categorized into one of these three things, like either node level tasks, link level tasks, or graph level tasks. For example, at the node level tasks, it would be interesting, or it would be important to predict like what's the user churn, what's the lifetime value of a particular product, what's the next best action that can be taken by a user. For link level, a very natural task that comes to mind is recommendations. Although there are a lot of ways to do recommendations, this can be casted as a link level task in such relational entity graph kind of construction. And also there can be some graph or subgraph level tasks which relates to whether a particular subgraph would lead to some point to some sort of money laundering, or what's the risk assessment of a particular subgraph of nodes, or maybe the interaction of nodes with user nodes with certain products or transactions. So so this construction tells a very I mean, this presents a very nice abstraction to represent many tasks and many domains in a very clear, unified setting, which is simply a graph construction of any relation databases and certain characteristics of graph, which is like heterogeneous, temporal, and the large scale setting. So, if we go to the next slide, we'll show like how we can enable graph machine learning on these kind of pipelines. If we just look at the top of the pipeline here, we have a relational databases that can be represented as relational graphs, and we can define the problem that we are trying to solve. For example, the node level, link level, or graph level, and then we can apply graph machine learning on top of it. Usually, the signals or maybe the training data for the each of the task node, link level, or graph level can be constructed from the data itself. That's called training tables. Like some of the rows that we are interested in. For example, if I'm doing a user churn task or user some user property prediction task, uh, um, some distribution, some data from the from the source databases can be converted to training table by considering some user IDs, and usually whether the user churns or not can be inferred from the function of whether the user has certain transactions in a particular platform. So this is one of the examples. But basically the pipeline looks like when we make the relation graph, we can also create the graph problem and its corresponding label from the relation database itself. And then once we have that, we have everything. Like we would have the graph, its number of nodes, number of edges, the column values of each of the entities, or each of the entity records represent the initial feature attributes of the rows, and then we can apply the graph machine learning pipeline. And with this construction, we get access to most of the innovation that has been done in the last 5 to 10 years surrounding graph neural networks. So, for example, we can use GCNs, we can use graph transformers, we can use heterogeneous temporal networks, etc. So it becomes a very nice application area for most of graph ML. Yes. So if we move on to the next slide, yeah. So far I was discussing what's relational deep learning and how relational deep learning becomes a very important graph problem, and for the sake of this workshop, it also becomes a very important temporal graph problem as well. Now, I'll give a brief background on how LLMs have been used recently for graphs. After which Fang will take and he will talk through the rest of the session. So, I mean, in the since LMs have become the very general, very universal world models, we have seen several works on using LMs for graph tasks. And what is key in any of such works is like the conversion of the graph into a prompt. So in this work, which is from Brian Perozzi's group at Google, if let's say there's a graph and a particular graph task is present, for example, whether what is the degree of a particular node in a given graph, the goal is to create an encoder function that can convert the graph information into a text prompt, and the question can also be associated with the text prompt. It seems very trivial, but this is one of the key ways that is used for using an LLMs to graphs. So whenever we have a graph, we can follow a particular template. I mean, that's shown in this case using the graph encoder function to describe the graph in the natural language that LM can understand, and the LM will be asked to answer this question. So this is a very early work in 2023, which is called Talk Like a Graph, that it tries to explore this and tries to find out what are the challenges of prompt engineering. For example, I mean, if let's say we are 20 people in this reading group, if we all try go and do the homework of trying to encode this graph in a text format, we may end up with all different kinds of prompts, and it will be very hard for us to reproduce the same result for the tasks, even if let's say we are all asked to use the same LLMs. So the prompt, how do we design the prompt is one of the key a challenge here, which also maybe later Fang will explain with some of the experiments that we did for relational deep learning as well. We also have other works in LLMs for graphs, which is in the next slide. Just to show like the challenge of prompt engineering. So this is another work that came from some collaborators from Snap Research, and then if we look at this example, they try to describe some template like where they can encode a node with their neighborhood. And they try to follow some sequencing pattern. For example, you can see. On the left top, like there's a neighborhood detail template that shows a node sequence as an output. They also adopt some padding tokens for cases which don't have the nodes there, and they also have show alternate methods of this. For example, the hop fill overview template where they take a node, then it's hop one, the nodes that are in the first hop, then second hop, and third hop, and so on. So they try to experiment with this kind of different designs, and then they convert the node sequence into tokens. In this case, they also use some different projections to consider different specific graph tokens, and eventually for the task they can ask the task in the text format. So this is another way of showing that I mean the key of applying LLMs to graphs is to find out the prompts. How do we design the prompts? And I mean, so far, like I would say on this area, the results or maybe the designs are rather maybe experimental. Maybe there's no deterministic way to define these prompts. If we move on to the next slide, I mean, same with the temporal task as well. So this is from Andy and his collaborators, which is again trying to follow a similar framework of encoding temporal graphs into prompts. And Andy and this paper also has some interesting results. One of the key here is to encode the temporal graph information into the prompts, and there are certain tasks that concerns with temporal nature of the problem, but also I would say like it follows a general I mean how to say general conversion of the input temporal graph to a format that the pre-trained LLMs can ingest. And I mean when we have this kind of framework, the LLMs can naturally be used to uh, uh, ask like I mean they can be used to describe like why they do a certain prediction for the tasks. But yeah, moving ahead, I think uh, there are several ways to there are several works in this direction like that tries to apply LMs for these graphs, and this is just to show some background. So far, like if I want to recap, like we talked about relational deep learning as a problem. What are the different tasks? How to do the construction? I mean, what the construction represents that can unify different data source domains, and how LMs are applied for processing graphs. So we move to the next stage where how we try to explore the question of how LMs can be used for relation deep learning, and maybe Fang can take up from here, and later like we both can take questions as well. So
Yeah, thank you, Vijay, and for great introduction. And I will take a lead. And first, let's go back to this question: how to process tabular data with language models. And this is a very excellent survey. Talks about what the practical implementations on tabular data. And since the tabular data can be pretty large, compacting them into fit context lines is necessary to achieve better performance and reduced costs. And traditionally, filtering and simplification are the very two common uh, mechanisms. And the filtering aims to reduce the number of rows and columns to be processed in large tables. And simplification, on the other hand, entails condensing the data by streamlining contents. So, what is the latest or the very recent algorithm to tackle prediction tasks in relational databases with language models? And this is from the Snowflakes. They they use convert the relational structure data to text prompts. However, there are some problems with this formatting. First is that relational or structural information losses can happen. For example, if we converting relational data into flat text, will obscure the unique relationship between tables, especially primary foreign key connections. This will reduce LM's ability to fully leverage the structural insights. And secondly, there will be a lot of redundancy in the construction of documents. If we construct prompts some prompts frequently, there will be scenarios that nested rules and interconnection relationships. This will introduce redundancy. And the third part, which is also important because in current large language model, especially not very large one with only less than 10 billion parameters, the context loss is limited, and you cannot put infinite text into the language models for as input. So however, the relational databases can include tables with numerous columns. Some contains serialized text. For example, in one of our relational database, the real Amazon things, there are a lot of customer reviews and representation a single row or entity in human readable language can result in a significant increase in input loss. So this will place a heavy burden on processing and the token limits of small language models. Besides, to tackle these three problems, we might try to do another different way from snowflakes. That is, as we previously said, we can transfer the relational tables as graphs, and rows in a table are nodes, and the primary keys connections are edges. And the different tables can correspond to different node tabs, and rows have some time steps. And so this will lead to a heterogeneous and temporal graphs of large size. And oh, sorry, there's some format mistake. If we have the graphs, the tabular table converted into graphs, we then use the graph encoder to convert the relational data into embeddings, and a graph network can be naturally leveraged to generate node embeddings. And a local subgraph is sampled with time awareness against the seed node and can be fed into GNN. And the output node embedding can be then fed into MLM. So this leads to our final framework. At the left side, a relational databases is converted into a graph into a graph, and the graph is fed into the graph encoder to attain the node embedding, and the node embedding is organized in serialized way. However, the difference is that currently the text is replaced with the node embedding, so this will significantly reduce the token length, and then we'll go through a projection and feed into a frozen attention layer of language models such as Llama, Quinn, any other types of language models. And so, interesting, there are two different things for us to do. First is the pre-training, second is the fine-tuning. I will introduce later. First is that in some scenarios when label data are sparse or absent, we might not be able to fine tuning the language model or the projection and the graph encoder completely. So we can do self-supervised pre-training to achieve the zero-shot prediction. For example, that is, we can use the node attributes of each in each tables as the unsupervised targets. For example, the income, the gender, the nationality, and the age can be the prediction target. And then after this self-super fine-tuning, we can do task-specific fine-tuning. Here we introduce, sorry. Here we do a small modification. That is, we find out the language models are not very good at outputting floating numbers because some decimals, some floating numbers are not one single token. They are divided into multiple single tokens. And for numbers more than for numbers more than three for some not more than three numbers, they are grouped into one token. So in that case, we just want to use MLP to predict the to for the regression tasks. And instead of this two-stage partitioning, we in fact try some different ablation studies, and we find out some attempts are not successful. And for example, this is one unsuccessful thing is in our previously slides, we used a low-level pre-training. That is, we mask the entire low in the in the tabular data and try to predict all node attributes in these rows. However, we also try some cell level masking strategy. That is, for like one customer, we only mask the age of this customer and keep the information of this, keep all the other informations of these customers, like the nationality, the gender. However, we find out this does not work very well because we believe that maybe only a subset of attributes is masked while others remain visible. Language models can often reconstruct the missing value by leveraging correlations across no attributes. This unintended leakage reduces the needs for deeper structural reasoning and instead encourage naive inference based on column-wise dependency. And also, entity-level mask will be more challenge and compel the model to develop a more holistic understanding of relational graphs rather than relying on shallow pattern matching. Another unsuccessful attempt is that we follow the conventional few-shot in-context learning algorithm in the natural language. Is that we try to use the to build many short contexts. That is the some node embeddings and give some ground truth labels as the few short context, and then to predict the target and without any fine tuning. However, we find out this does not work as well because and how to explain this phenomenon? We believe that language models predictions. This is also found in Snowflake's paper that are very highly sensitive to the choice of in-context examples, and we'll show with more quantitative results to of the as proof. And the performance varies considerably depending on the specific selection of example. Oh, there's some uh, text, right? Sorry, I cannot see it. And maybe we can answer later. And this instability aligns with observation from prior study, as I said. And this sensitive may stem from models' inability to effectively aggregate information across many node embeddings. And so maybe further some future research is needed to disentangle whether the issue arises from suboptimal prompt construction, insufficient adaptation of GN-derived embeddings, or some inherent limitation in language models to generalize from structured input representations. So what is our final results? We can see from this table, our real LM achieves the highest average AURC, and which outperforms the relational deep learning RDL and in-context learning plus the multi-layer perception. And however, in F1 drivers, their historical performance are well documented in large-scale tech corpus used for language model pre-training. So sometimes the in-context learning plus the multi-layer perception performs pretty well in this real F1 dataset. And however, a key limitation of in-context matter is that the dependency on the quality order and the quantity of in-context examples. It is also constrained by the context loss limits, so this will making them sensitive to prompt design. And however, so instead, our measures eliminates the need for explicitly providing texture in context examples, and we can also generalize using only its prior pre-existing knowledge by passing the need for manual annotation. So this is the rel 01, which is with only the first self-supervised stage. And also in regression tasks, we found out we also consistently achieve the lowest mean absolutely error, and this highlights the strong generalization capability across diverse regression problems. And so by integrate graph-based entity reasoning, our method effectively captures long-range entity dependencies, enhancing its robustness compared to the heuristic approach and traditional machine learning methods. So some more results due to the the computational resources, limited computational resources, we do not perform like much larger, like 10, more than 10B or 17B or billions, hundreds of billions. We just increased the model size from 1B to 3B, and we found out generally outperforms the 1B model across more tasks. However, the gap is not very big, and notably, 3B demonstrated more pronounced improvements in the rel F1 tasks, where its larger capability allows to better leverage the pre-training task of knowledge, particularly in scenarios require complex reasoning or deeper contextual understanding. So these so let's talk to the final limitation and the future work. Um, the graph encoder in current RLM is not a general graph foundation model, and this is currently also Vijay is currently research on very promising direction. And also the graph encoder depend on individual databases and tasks. Maybe we need a unified graph encoder that can be generalized to diverse databases and tasks, and also the database row level encoders as I said, not generalized due to the dependency to columns in specific tables. And finally, the graph encoder is graph neural network based. While currently the latest or the advanced studies show that maybe graph transformers is much better at graph learning, and we can replace this graph encoder to and one more thing, maybe I can add it, is that how can we make this language model with string of thoughts? We can do reasoning instead of only the simple direction. Sometimes people want to know why language models achieve this answer, and at our current version, we do not have these things to be trained because maybe we need some reinforcement learning with post training instead of only the self-supervised tuning to allow language models to thinking. And we hope that future followers and researchers can fill this gap. Yeah, thank you. This is my presentation.
Yeah. Hi, Fang. Actually, I think Zach had a very nice question. So maybe we can go ahead, go before, and then do a walkthrough of the model a
Yeah.
bit in detail. Like we can show like how we have the relational database where we do the subgraph sampling. What are the different ways to that we use to encode the graph information in there. Like, maybe we can go back to the architecture and then have a walkthrough again. Yeah.
Yeah, okay, no problem. Yeah, what is their question?
Um,
Yeah, so I'm just trying to understand, like, for example, you have this kind of JSON looking text at the bottom feeding in, but we're also talking about GNNs. So, like, where's the GNN feeding into this, and what is represented as text and tokenized and so on? I'm trying to understand this diagram.
Oh, I see. As we previously said, uh the we have a graph that is has already converted from the tabular data, and the graph will have like we have a seed node, which is our like the target user. We want to predict the information of this target user, like what will the action of this user in the next 10 days. And it has some historical transactions, which is R1 and R2. And the P2 is what they buy in these transactions, the products. And so we can convert these graphs into a format which is currently uh, in this way in a nested way, that seed is the starting point, and then it follows with its transactions. And in the original way, it is a text version, right? The customer ID, the timestamps, and it buys it has name, JS transactions. However, this is pretty long, as I said. So we convert it into by the node embedding. So the node embedding is only one token, and so this keeps the original relationships in the graphs, but in a more clean and condensed way with the node representation. And then it is feed into the projection to the graph encoder. The node representation embedding is in a different embedding dimension, and we need to align it into the LM's no, LM's hidden space dimensions. And so this will be the input along with the text embedder. The text embedding will also include some data and task descriptions. For example, what's data like real Amazon is a data that records the historical transactions of customers, and what is the task, like what will this user be active in the next 10 or 30 days. So this sort of information is input in human language as the text prompt, and then all these things will fed into the attention layers, and finally we'll use the final tokens to predict the node attributes in the self-supervised pre-training stage, or in the fine-tuning stage, that we will be some other specific tasks. Yeah.
So one last question. That's very helpful. Thank you.
Sure.
In the diagram coming out of the projection box, there's the masked node and then there's neighbor nodes. But my understanding from your explanation was that there's a single embedding for the seed node as a single token coming out. So what are all those yellow boxes?
Oh,
If
yellow boxes. This just means that you mean the seed node is different from those yellow box?
I thought you said that the GNN gives us a single embedding, which we then apply a projection, and now we have one token that represents the entire graph around the seed node, was my understanding. But then I don't understand what these yellow boxes are in that case.
Oh, just to provide some yeah, in fact, in our graph neural network, since we have to already do the graph convolution or some neighboring aggregation from neighbors, so this seed node has already get some local subgraph information, but this we just provided those neighbor like pink or blue one with specific design. So this yellow is just with to manually provide more neighbor information, and the yellow is just after the projection. I just color them with the same with the same color. Yeah.
So
Yeah.
every neighbor is a token also?
Yeah. So I was coming to that actually, Zach. Thanks for the question. So actually, for example, here, just to add on what Fang mentioned. So if let's say the graph encoder input has a graph of 100 nodes, so the graph encoder output will be 100 nodes, and these 100 nodes will be the input embedding tokens. And the text that's present here, like the serialization, textualization, and the text example that you can see, it's not the text actually, but instead it shows that the embedding corresponds to this text that was present in the original databases. So oh, sorry, maybe Fang, can you put the
Sure.
screen again?
Sure.
Yeah.
Oh, sorry, I don't know why it.
Yeah, but the idea was like the graph neural network comes into play, or the graph encoder comes into fit in the picture, is that it's converting the initial original graph that we have into if let's say we have 100 nodes, we'll have 100 token embeddings. So it's simply like 100 times t, and all the yellow nodes correspond to that. There's a specific mask node that we have for the seed node that shows like I mean, this is something that we mask to do the pre-training. So that's maybe some additional detail. But overall, the graph encoder, the goal of it is to feed in the soft embeddings, or maybe the embeddings of the each of the nodes. It can include the seed nodes as well as the neighbor nodes as soft tokens for input to the GNN, for input to the LLM.
I then have a follow-up question on this. When you look at the yellow boxes, as Zach pointed out, so the order of these yellow boxes, is that kind of derived based on the relational entity graph, or how do you kind of set the order of the neighbor tokens there?
Oh, you mean how the these neighbor nodes are ordered, right?
Exactly, yes.
Yeah.
Because in language, order can mean quite a lot, but maybe if you're looking at a graph, then how do you kind of make order it?
Yeah, maybe for like transactions, we can like manually rank it with the latest like the by the date that is close to the current date by order. However, in some cases may not have this very logical ranking, so we randomly like order them in for their close neighbors. Yeah.
Thank you.
Yeah, this is a very good question. Maybe we can, consider it later in further in the next version. What's the question? The node embedding. Yeah, this is very interesting question. We can replace each node embedding with the most similar word. Um, yeah, this is like we can very similar like VAE, like VQ VAE to transfer the node embedding into the word embedding. However, um, we do not know whether this will works because the word embedding each word token just is limited, but maybe this node embedding includes all the information of these users, these customers, and might be a little bit difficult to convert into one discrete tokens in the tokenizer, I suppose. Yeah.
I have another question, and that's kind of, maybe comparing the different approaches when we're discussing this LLMs for relational deep learning. So if you go back to one of the Google paper where they kind of have yes,
This one?
exactly this one. So if we're comparing your method, or kind of where we use a GNN encoder and then kind of take the node embeddings and put that into the context of the model versus this approach, right? I guess that in your method, you're throwing some compute at it, right? You're basically kind of fine-tuning the large language model to optimize for like a predictive task that you think is similar to the one that you're going to be using it. Whereas in these papers, are they fine-tuning the models? Like if you threw as much compute on this approach than as the GNN encoder approach, would we maybe see similar gains, or what's your opinion on that?
Oh, you mean if we can directly use the in these talk like graphs, we can also fine tune the model, you mean? And
Exactly, yeah. So if you just, in your situation as well, if we just take, the sampled neighborhood and we serialize it, and then, we just fine tune on the serialized data rather than doing this GNN encoding.
yeah, actually we haven't done that because yeah, but I believe your intuition might be correct because this one though due to the redundancy, as I said, it has some pros and cons. The pros is that we can fine-tune it directly without introducing a graph neural network, without aligning the different hidden space between graph and the text. And we can also do reasoning things because language models can directly output the reasoning, and we can maybe directly using reinforcement learning with the verifiable rewards. And if the answers matches, then we give a positive rewards. And so the reasoning chains can be reliable and explainable. However, the cons is that as we said, there can be a lot of repeated things. You can, even we want to, even in this naive way, we want to describe the connection. The node one is connected to node two and three. How about like there are a lot of very complex relationships, and you have to spend a lot of tokens in just describing the connections, right? And no need to say, as we said, there are a lot of like transaction IDs, customer IDs. And for example, these customer IDs, you can see very straightforward. Customer ID has to repeat it multiple times because in each transaction and some other, items and things should be repeated. So I'm not sure if we want to fine tune a very small, relatively 1B or 3B models.
Mm.
Maybe the context will already be very long, and the models may not be. When the context is pretty long, might be difficult to understand the context. Yeah, trapped into the understanding. Yeah.
Yeah,
Yeah.
maybe I'd like to add on this question. It's very interesting question. Thanks, Victor. I think, yeah, the context length problem, like as Fang mentioned, it remains. But I'm not sure whether this paper specifically does any fine tuning. If I recall correctly, they don't. And maybe this is a way of showing that the graph encoder function can convert input graph to a texified form, and it can be used with whether the LM is open source or closed source. Maybe even through an API it can be used. But I feel like if I were to guess whether it should work, for example, we can construct a data set of different graphs. We can convert them into text prompts along with the graph task associated with the input data sample. And if let's say I were to take an LM and maybe fine tune on a very good data set of such like input output pairs, I will have the texified graph, and then the output will be, for example, what is the degree of the node force? So maybe something like that, about this as the output. I'm sure it should definitely improve and maybe close the gap, because like you mentioned, the core reason behind this can be that we are throwing additional compute to the model if we were to do that. And I feel like that's a very interesting point. We didn't explore that. We do have some in context learning results which Fang was mentioning earlier, but I feel you raise an interesting point where like when we compare this kind of models versus fine tuned with a similar texified prompt, I'm sure like there should be some gains in the fine tuning using the additional data samples. Yeah, and to kind of motivate the overall architecture, maybe Fang, if we can go to the main, maybe page 17, the additional architecture. Yeah, to motivate this additional architecture for those like maybe still you feel it's not clear. I think we take a lot of motivation from like the way vision embeddings work in VLMs. So what's if I were to take this figure and then understand vision models, like let's say the relational databases, replace this with images. So we'll have images here. Then images will be converted to the soft embeddings, like images can be converted either through some discrete visual tokens, or maybe continuous embeddings. It's done usually with the vision encoder. That's again a transformer based model, and that vision encoder is a general vision foundation model pre-trained on large scale of images, so that it gives the embeddings in a very general manner. In this case, I would say is this kind of work that we do is one of the steps towards in that direction, where we can show that if let's say we have multimodal input and we want to interleave embeddings with the LLMs. This is one of the way to do that. And the graph encoder in this case is not a foundation model, but let's say if hypothetically tomorrow we have more general graph foundation models, this is one of the ways we can process either input graphs or maybe relational entity graphs through the graph encoder, and we will get some soft prompts. So we'll get some embeddings that can be used as soft prompts as prefix to an LLM. So we're trying to follow like that direction, and I feel like this is a very early result that we got, which could be a better way compared to simply textifying, because here we are trying to incorporate the relational structure information through a model that understands these relational structure information explicitly. If let's say this graph encoder would be more general, more like the general graph foundation model, which we've seen, like there are three results recently since May or June-ish. I think if we have a general graph foundation model, the embeddings here would even squeeze out most of the input relational structure information from the data. So that's there are parallels to the studies coming from the vision models. Yeah. But thanks for the question, Victor, and others as well.
Of course. I can ask another question if we need to pass the time. So I'm a bit curious. I think you jumped a bit over the pre-training paradigm here with the green box. If you go back one slide with having it fill out the gender and age. So is that kind of the focal? You basically select a random node, like a key node, and then you mask it out, and then you use it to predict those, or? Oh, I think you're muted, Fang.
Yeah.
There we are.
Yes. For example, like originally we want to predict the future actions of this seed node, and in the pre-training stage, then we do not have the task specific questions, so we just mask the attributes of these nodes, mask all the attributes of these nodes like gender, age, nationality, and so this is only a mask token, just similar in mask language models. Yeah. So we just recover all the informations in text, like ask them what's the gender, age, nationality, income. So just to do the unsupervised training without any ground truth labels. So labels come from itself. Yeah.
All right. Cool.
Thank you, Victor.
Um, and two questions. One is related, but also not too related. So Vijay, when you're working on the relational graph transformer paper, do you observe this setup has better performance than relational graph transformer, or like the other way around, within the same set of parameters, like within the same weight class for parameters, which will be more efficient?
Yeah, I think there are marginal differences in performances. In some cases, relational graph transform is better. I think the REL LLM work is when we compare to the RDL baselines as well, and maybe Fang, you can correct me if I miss some details. But compared to the RDL baseline, there are only marginal gains that we gain from this paper from the REL LLM work. But the overall goal was to show like what's the understanding of using large language models on these relational databases, and how does it compare with simply textifying or maybe using few short ICL. So with this, like compared to the GNN RDL baseline, REL LM improves marginally, whereas compared to the same baseline relational graph transformers, maybe slightly more. So there's maybe like this is RDL, this is REL LM, and this is REL GT. So slightly the REL GT has better performance. So yeah, ideally we can replace the graph encoder. So this work predated the REL GT work. So that's why we don't have the REL GT experiments to show in the graph encoder. But yeah, maybe that's the overall trend, I would say.
Yeah, and to me, so last week we have the talk on TG Talker, so this week we have this talk, and then next week we have a foundation model for temporal graph talk, so all kind of in the same theme. But basically, I think for using LLM here, I think the most interesting part that it can do, but GNN cannot do, is the kind of explainability part. And then I know that for most of the tasks in Railbench, it's very node centric, right? It's node classification kind of, or like a link task, right? So I'm also curious because now let's say we have some subgraph level tasks, as you talk about like before, Vijay, like let's say we want to predict total sales. What kind of natural language reasoning can the model provide now when it can perform decently well on this task, right? So can it tell us something about the subgraph, or can it tell us something about total statistic, like what kind of reasoning it will provide? So for the link level task that we did in TG Talker, we see that the model mostly try to mimic a lot of heuristic for link prediction that we have in temporal graph, like kind of what are my past neighbors, what are my most frequent destinations, and yeah, and also like counting some sequential patterns and these so on. But it's very like local, right? So I'm just curious, like maybe as kind of a future direction is like when you have this good architecture as you have right now, what kind of reasoning can we ask about subgraph? Because it's even not clear for human to think about, right? So you want to make a subgraph prediction task, like what kind of reasoning or algorithm to even do for that, right? So I think it's like it's like very interesting to let the LM to explore this task and see what kind of reasoning it can give, and see if it can go beyond kind of just the neighbors, right? Can it say something about the subgraph directly, or
Hmm.
yeah, but yeah.
Yeah, thanks, Andy, for the question. I think there was one related question in chat as well, which was towards the explanation, and I take few points here. One is like the evaluation here that we had was basically predictive tasks, and there are 30 different tasks in Railbench, 21 of them being node centric, and remaining like nine are more link level recommendation tasks. So because of the fact that we didn't have like subgraph level benchmarks as well as explanation level benchmarks, we did not have any evaluations on that. But I believe like let's say if we were to ask we were to apply this in a similar setting where we have enough signals surrounding subgraph labels, some enough labels surrounding subgraph, we can have the prompt to answer these kind of questions as well, because the subgraph is if we look at the overall pipeline, the subgraph is being converted to embeddings. These embeddings are used with LLMs, so these are kind of encoding the understanding of the input subgraph. So if we can revise the task description to predict something on the subgraph level, and maybe if let's say we have labels surrounding, we can even fine tune, we can definitely achieve that as well. And yeah, it can be an interesting future direction to explore. I think the challenge we had was like the benchmarks, and this is the key reason we were not able to evaluate the explanation as well as the subgraph level task. But I imagine like it's a very trivial extension, and the same framework can be used to benefit like these kind of application scenarios.
Yeah, thanks. But actually, just one last word on that. For
Yeah.
explanation, we nobody anywhere have any label for that.
Yeah, I
Maybe
mean, yeah,
out
evaluation labels.
where you can directly attribute and could take years of process to find out who caused the anomaly. But maybe beside that, there's zero labels whatsoever because GNN do not provide explainability. So it will be a
Yeah.
brand new direction only LLM can do, and how to rigorously understand and generate sensible, plausible explanation, right? Because if you're doing predictive tasks, there is no ground truth for why this prediction should be this way. But it's more like, does the generated explanations are sensible or not, I guess. So it's, but
But
that,
Yeah. Yeah, I agree on that. Um, Yeah, maybe before Victor can mention, I just saw a question from Zach, and then I just wanted to maybe mention a related work. I remember there's one work that has tried this for other Genian tasks. The paper is called Graph Neural Prompt. It's from the group of Nitesh Chawla at Notre Dame, and I think if I remember correctly, that work has a very similar pipeline where the input graph can be converted into soft tokens, like soft prompts, into such embeddings. But maybe that work is a bit maybe 2023-ish, and they were not like it's very hard to directly compare, and because like the way how LLMs are moving so fast, and the models that are being available to us are maybe during different time. But I feel like, yeah, the closest work that is called graph neural prompting from the group of Nitesh Chavla. Yeah, yeah, Victor, please go ahead.
No, I was just thinking, along Andy's question about the explanation, and Fang's comment about that many of these tasks are actually verifiable, right? So I guess you could kind of train sort of a model and then look at its reasoning trace and then see, oh, it was because of this and this node or that and that. So that could be cool. But yeah.
Yeah, very difficult to do in practice.
Yeah, I mean, yeah, we can definitely definitely have the prediction signals that we can use to do kind of a verification, but yeah, I mean, how do we measure, like, I mean, I was thinking I was coming from the place where I was thinking, like, how do we measure the explanations, whether they make sense, or more sense or less sense? Yeah.
Well,
But I agree with your point.
it doesn't help you
Yeah,
guys
Sam.
with open data very much, but at least in industry, like in fraud detection tasks, we often have investigators who take notes and mark down, like, we're shutting down this person because they're connected to these people, so on and so forth. And I'm sure that data could be helpful for this sort of thing, but unfortunately, you can't share it.
Yeah. So that's my intuition as well. Like anomaly detection or kind of these tasks would have some sort of signal that which should be the ground truth. But other than that, if you're just predicting why you should recommend this item to someone, then there's no ground truth. Like it's just like, okay, this is something that they like, because the user themselves don't know until they see the recommendation, right? You can probably get some downstream signal, but it's not like very easy to do. Okay. Cool. Thank you, everyone. And we're at the end of the hour, so let's wrap up. Let's thank our speaker again for the great talk and the great discussion. And yeah, thanks everyone for joining. Yeah.
Yeah. Thanks, Andy, and thanks everybody for the question and discussion as well.
Yeah,
Bye-bye.
thank you. Bye.
Thank you so much.